my name is Alex Shluger, and so I'm a professor in UCL. And I'm organizing this course, and everything what you see, basically you can talk to me or to Karen. So Karen is the manager or administrator of TYC at UCL, and basically administers the whole TYC at the moment. And so I'm the director of TYC at UCL. So and organizing this course here. So today we were supposed to have a lecture by David Bowler, which was supposed to be on basically introduction to DFT. But two things happened. One is that train drivers went on strike, and so David couldn't come by train from Cambridge, where he lives. And so therefore we set this lecture online, not to miss it. On the other hand, David got sick, and so he couldn't give a lecture. As a result, I'm going to tell you something. So this is a lecture which I used to give for many years before, trying to put you all on the same footing, because I understand that many of you come from completely different backgrounds. But the course is quite a complicated course, which is supposed to provide you some basics of density functional theory and then other things, which we'll go through now. So therefore, today we will try to talk about the basics of quantum mechanics and see how it will go with you. So first of all, let me thank Karen for setting this all up. And so she will be the first point of contact for you. I hope to see all of you at the welcome event on Thursday next week, where you will be introduced to TYC. So a materials modeling course is only one thing which TYC is doing. So there will be a lot of seminars, workshops, conferences, and other things which you can attend, apart from talking to each other and discussing things. So the purpose of this module, which is not examinable so far, but is quite thorough, and so goes through a lot of material, is to give you some basic understanding which is required for your research. So basically, in the first term, we'll talk about things which are related to atomic scale here. I guess you can see my my pen here, and then we will go further up in scales. So scales is an important part for many of you, because some of you will be doing DFT and will be doing some things on a quantum scale and quantum level, and some of you will be doing some classical simulations and also maybe some biomolecular simulations which go further up in scale. So this module will cover, on one hand, quantum part, and then at the end of this term and next term, we also will talk about molecular dynamics, kinetic Monte Carlo, and other things which are required in order to look at, say, dynamics of systems, and also mesoscale. So looking at, say, big molecules, etc. We are not covering this part, so like crystal plasticity in this module, but say then by that time when we will learn these things, you should be able to do it by yourselves. So now, the methods which we are going to deal with are basically these type of codes like CP2K, crystal, WASP, Gaussian, etc. And so in the next several weeks, you will get introduction into that. And then also other types of methods which are dealing with, say, classical molecular dynamics, like, say, SHARM and others, as well as various types of force fields. Then we talk about Monte Carlo, and then come to mesoscale. And so all of that is organized in this type of schedule. which most of you should have got, or if you haven't, then ask Karen to send it to you. So today is October the 4th, and so we're having this lecture. Then on October 11th, Dave Bowler hopefully will come along and will be able to tell you about Hartree-Fock approximation, and then basically talk about main electron systems up to some density functional theory. And then for 3 weeks, you will also have discussions with Tom Durrant. So all of that are going to happen in person in E37. And so Tom will take you through basically details of DFT calculations. So it's periodic boundary conditions, pseudopotentials, electrostatics in DFT, total energy calculations. So how do you do all of that, say, in detail? And then on November the 1st, two famous people will come along. So this is Furio Cora and George Booth. And so they will tell you how to go beyond DFT and how to go beyond Hartree-Fock methods. And after that, you will again meet with Tom Durrant, discussing about practicalities and geometry optimization methods. So basically by November the 8th, you should be up to scale with DFT simulations, so which should give you some reasonable start for you to start doing some calculations yourself. Of course, you can do it in parallel using various codes, say WASP, or many of you will be doing, or CP2K, or say other codes available in your groups. And then from that time till the end of term, you'll be basically exposed mainly to molecular dynamics, different techniques, and also Monte Carlo. And so these will be given by various very also well-known people, like Johan Blumberger, Dina Rosta, and Matteo. So some of you are their PhD students, so you will be also able to see how do they teach other people. And so after that, there will be Christmas, and so you'll be able to say basically revise and digest all of that. And then in term 2, we work on more advanced topics. And so first of all, Dorothy Duffy will talk about interatomic potentials. And so what are types of interatomic potentials available? And then Ian Ford will discuss about kinetics and thermodynamics of nucleation. And after that, Johannes Lischner will go through electronic excitations. And so this is quite advanced technique here. So GW and beta salpeter techniques, which allow you to calculate also electronically excited states. So after that, there are a couple of lectures by Venkat Kapil, who is very famous for machine learning, for deriving force fields and interatomic potentials. And so he will spend, say, 4 hours explaining you about how to do that, and also about quantum statistical mechanics. And at the end of that, we have 4 types of lectures. So one is given by Lev Kantarovich from King's College on vibrations in molecules and crystals. And then Dario Alfe will talk about quantum Monte Carlo. And then Angelos Michaeladis will talk about accurate ab initio simulations. And final lecture is always given by Chris Picard. So who is going to talk about high throughput calculations of and structure predictions. So altogether, by Easter, so you should have a very detailed overview of how to do things, and try to apply that to your own simulations, right? So this is the idea of this module. So obviously we cannot cover everything what you may be doing in your project. So that will need to be covered either by some special workshops which you may have, or by your supervisors, or by your discussions in groups. So do you have any questions so far about the course? Yeah. So I see there is something in the chat, but I don't see. Do try to switch on cameras if you can. Great. Okay. So any questions? Don't see questions so far. Okay. So then let's move on. So how is it going to work? So I told you, so this is going to work as face-to-face lectures mainly. So today we are basically victims of a train strike, and so therefore it's not face-to-face. But say it should be face-to-face all the time, say over the modules, unless say new train strikes or something happens. Right. Okay. So now what I wanted to do is to go through some revision, and particularly I wanted to go through the origins of atomic orbitals, because this is the basis of everything what you are going to do in the future. Say even if you do molecules or if you do crystals, whatever, so you'll be dealing with basis sets which are basically atomic wave functions. And so these atomic wave functions are represented either in the form of what we call atomic orbitals or plane waves. So what you will be having is usually either some atomic orbitals, say functions like what we call S, P, and D functions, which you'll be combining together into some what we call linear combinations of those. Or you'll be dealing with plane waves, which are more general basis sets, which are used in order to represent the behavior of wave functions of electrons in materials, solids as well as molecules. So, for example, in WASP, we use plane waves. In CP2K, we use a combination of what is called local orbitals or atomic orbitals and plane waves. Right, so this is how it works. So therefore, it's important to understand the origins of that. So it would be useful to understand, but I cannot see that clearly, how many of you did physics and did some quantum mechanics courses in physics, which basically give some background for this, and how many of you did chemistry and other types of disciplines and are not particularly familiar with that. So I would like to see that, but I'm not sure that I can really. So can people who did actually physics say put their hands up?
Actually, I did mathematics degree, master's in maths degree, and theoretical physics subjects like dynamical systems, ergodic theory, yeah, quantum mechanics. Yeah, but it's nothing really too deep in physics, but I'm reading now about other areas of physics because there's an overlap with my area of research. So I'm learning all the other intersections needed.
Excellent. Okay, so I can see that 9 people out of 33 raised their hands, saying that they kind of studied physics, and so then this tells me that 24 maybe didn't. So this is the reason why we may have this lecture, actually, to try to put all of you on the same footing. But it is a little bit mathematical, which is quite useful also from the point of view of what you have been doing before. So for some of you, it is just revision. So the first thing to understand is that in quantum mechanics, we operate with postulates, right? So the quantum mechanics is based on several postulates, and so if so, something what we assume. So if you read different books, you may find a different number of these postulates, and so they may be formulated a little bit different way. But say generally, what we're talking about are these postulates of the type I'm going to talk about now. So first of all, we postulate the first thing that there is a wave function. And so we think that this wave function completely specifies the state of quantum mechanical system. And so this wave function depends on both spatial positions of, say, our quantum mechanical system and time, right? So that is an important first postulate, which we are using all the time. And so we will apply it in a minute. So it may be a single electron, for example, or it may be single neutron or any quantum particle. We describe that by wave function. But we also describe by wave functions what we call many electron systems. So many of you will be studying, say, crystals or some other types of solids or biosystems, some biomolecules, etc. They contain many electrons. Still, each of them is described by their wave function, and the total system is also described by a total wave function. But in that case, that wave function will be a function of coordinates of all electrons and still will depend on time. And so now, how do we link it to reality? So we introduce a property, which is this product here. When we take a complex conjugate of the wave function, multiply it by the wave function, and we say call it probability that there is a particle located at some position R in a volume, a very small volume, which is defined by X, Y, and Z at time t. So basically, the idea of having a wave function is, say, so this is one of the interpretations of that, I must say, is that it describes the probability of finding our quantum system at some position at certain moment in time. And so basically, in this way, the wave function contains all possible information about the particle or about our system, but an important question is how to extract this information. And so for that is what other postulates are given. So the probability density is described. So say, for example, if this wave function looks like that, and so its square modulus, or the product of what is called a complex conjugate and the wave function looks like this, and when we integrate it, then we can say, okay, so in this interval, the probability of finding our, say, particle is, for example, equal to some number, 0.93 in this case. Yeah, so this is a mathematical nature of this construction. Right, so then people have introduced the second postulate, and so that postulate is based on several important physical notions. So one is notion of observables. So we need to observe something, right? So what are these observables? So these are position of atoms, say their momenta, energy, and say other things, which we somehow want to measure because we want to observe them, right? So, and so the postulate number 2, says that actually all these observables are represented by Hermitian operators. So that is an important thing in quantum mechanics, that instead of, say, for example, momentum, we have an operator, meaning there is some action by which we act on the wave function. Usually it is differentiation or product, which substitutes our classical observable. So quantum observable is an operator which is acting on the wave function. And the order in which operators are applied to a function is important, and it's not always that we have the same result if we apply these operators in different orders. So, for example, we can apply it say B on acting on the wave function, and then let A after that. Or we can apply A first and B after that. And so the action of these two operators may give different results. And this is what is shown by inequality here. And so this quantity, which is called AB minus BA, so when we act with this on the wave function, is called the commutator. And so that is a very important quantity. So in physical terms, it is usually written like that. So AB minus BA. And so usually we apply it to the wave function here, and we see what the result is. And so if this commutator is equal to 0, so that means that actually the result is the same, independent on the order of application of our operators, then we say that these variables, or these observables, commute. So comes from the word commutator. And so that is an important physical property, because if they commute, we say that actually they can be also measured simultaneously. So we can know about them simultaneously. We can measure them simultaneously. And so this does not apply to, for example, position and momentum. So they cannot be measured simultaneously. And so this is a formal expression of Heisenberg uncertainty principle, right? So we know that actually, say if we know everything about the position, we can know nothing about momentum, and so, or otherwise we can know something about position and something about momentum. So I guess that is familiar to most of you, or to some of you. Does it make sense? Do people have questions about this? So these are, remember, so these are not results. So these are postulates, right? So we postulate, and then we build theory on that basis, right? So I'm going to show you how we do that. And so how do we arrive to orbitals, and how do we arrive to what many of chemists say have seen already, some type of p orbitals and d orbitals, which we are going to use in our theory. But so far, can you manage this? Do people have questions? Don't see much, but don't be shy. So the purpose of these meetings, particularly the reason why we wanted to have them in person, is exactly that you can talk to the lecturers and ask questions, and say interrupt if you don't understand, or tell what your problems are, because if you are, say, most of you will have the same problems, and so the same questions. Just one of you should ask these, and then the rest will be grateful that somebody has asked. But it's important to get it out, right? So don't hesitate to interrupt me if you have any questions. Now, then there is another postulate, which basically tells us how we are going to construct our theory. And so in the previous postulate, we said, okay, so there are operators. And so every observable is represented by, say, this operator, which we call Hermitian operator, because they satisfy certain conditions, as we'll see. But now we say for each and every Hermitian operator associated with an observable, only certain values of this observable are possible. So this is nature of quantum mechanics. So in particular, they must satisfy this type of equation. So many of you have seen this equation. So this is what is called eigenvalue equation. And one of the equations of this type, if we use Hamiltonian instead of this operator here, it is called Schrödinger equation, where this wave function is a wave function of the system. And so why we use this Hermitian so-called operator? So this is comes from the name of the mathematician who introduced this type of operators. is that these type of operators have eigenvalues which are real. So we want to have real numbers to compare with say with some observables in real life which we can measure, because alternative would be that these eigenvalues will be complex, and so complex numbers are much more difficult to compare because what we measure usually are real numbers, and so therefore it's important that the operator representing our systems is Hermitian. And also for so-called non-degenerate system, eigenfunctions are orthogonal. So that means that actually when we take a integral of complex conjugate multiplied by the wave function and integrate it over the whole space, it is equal to 0. And so it's, these wave functions, eigenfunctions of these operators are orthogonal to each other. So also because the wave functions are probability distributions, so we have what is called normalization condition. So that means that actually if we take this type of product, which describes as a probability of finding our particle in particular space, in a particular point in space, and integrate over the whole space, we should find it somewhere. And so the probability altogether should be equal to 1. So this integral is called a normalization condition. Apart from that, it also can be proven that eigenfunctions are complete, meaning that say any functions, any state wave function of the system can be decomposed into some of the eigenfunctions. So this is quite a big mixture of different mathematical terms, but I hope that you can cope with that because this is what basically this module will be using all the time, right? So when we talk about plane waves, or when we talk about, say, atomic orbitals, etc., we will be using these conditions, that the fact that, the wave functions are orthogonal to each other, or say that they are normalized, etc., all the time. So it's important, to digest this, and if you feel that it's difficult or you haven't encountered this before, I guess you'll need to read some books about this to be able to follow the rest of the module. Does it make sense?
I have a question.
Sure.
Is the only conditions that determine whether an operator is Hermitian both that the eigenvalues are real and that the eigenfunctions are orthogonal? Is that what makes it Hermitian, or is it Hermitian?
Yeah,
it
is. I mean, it's the same thing. So by definition, Hermitian operators, they have real way eigenvalues and orthogonal eigenfunctions. There are all sorts of other types of operators, and they don't satisfy this property. So therefore, in quantum mechanics, because we would like to, it's not a mathematical theory. It is a theory which is linked to experiment, right? And so for this theory, we want to produce something which can be compared with real life. And so therefore we choose on purpose this type of operators, Hermitian operators, to represent our observable. But there are other types of quantum mechanics, and there are other types of theories, and so they operate with different types of operators, and some of them are kind of much more general than the quantum mechanics which we are talking about here. So you need to be aware of that. So on the other hand, the quantum mechanics is not the kind of final theory, so it may be even wrong. So therefore, we rely on you to develop new theories for that and come up with some new suggestions. Is that clear?
Yes, thank you.
Right. Okay. But these are not the all postulates. So there are more others. So, so one of them is postulate 4. We talk about expectation values or average values of observables. Say, for example, what is an average value of position of particle in space, or what is average momentum, or what is indeed its energy. And so each of them is represented by operator, but how do we calculate this average value? And so the way how we calculate this average value, we postulate that the way how to calculate the average value is given by this formula. So basically what we do, we take complex conjugate, then we take an operator, act by this operator on the wave function, and then multiply by complex conjugate, and then we integrate it over the whole space. And so that is supposed to give us an average value of that observable over space and time, right? So this is, again, a postulate. Yeah, this is how we suggest to build up this theory, that when we ask this question, we use this operation to do that. And then we also have another postulate, which tells us about what happens if things have changed in time, temporal evolution, right? And so we say, okay, so then we are going to use this type of equation. So this is time-dependent, what we called Shluger equation, which takes also a derivative of our wave function over time. And H, like in classical mechanics, stands also for Hamiltonian, but in this case, it is an operator. And so it is, again, written in the same way as classical Hamiltonian. So it has kinetic energy and potential energy, but both of them are represented by operators. Right? So these are complex bases or postulates which we use in quantum mechanics. And so now let's try to see what it has to do with atomic orbitals. And so how do we get to these shapes? So many of you, I guess, have seen these shapes because this is the language on which physical chemistry and inorganic chemistry, organic chemistry, and many types of chemistry, as well as atomic and molecular physics operate. So basically, these shapes represent probabilities of finding electrons, say, near some nuclei. So for example, say if there is in the middle, here there is some nucleus, like for example, a proton, we talk about, say, S function, or the wave function which describes the behavior of electron around this nucleus. And so it has this shape. So, or we have so-called p orbitals, d orbitals, etc. They have these particular shapes. And so the question is, where do they come from, all these shapes, and why these things are so powerful for describing, say, properties of molecules. And so atomic orbitals and this type of behavior are basically, language of quantum simulations. Whatever you do, even if you'll be using some plane wave codes or something like that, you will need somehow to express, what you have found. So, for example, you have calculated some complicated crystal or whatever, but or some complicated molecule, and you will need to explain how actually atoms in that system talk to each other. So that means that you'll need to use some language of bonds, right? So say you need to say, for example, atom, say titanium atom forms some covalent bond with oxygen atom. And so this is why this system is stable, or two carbon atoms form, say, some covalent bond, or say they form some pi orbital or something like that. So this is the language on which we describe things and write our papers. Because it is accepted by the community. And when you say that, okay, so here is, say, a covalent bond, or say some ionic bond, or here is a metallic bond, or there is some p type interaction or something, people immediately know. So you don't need to explain further. This is because it's a language. So people immediately know that actually, okay, so say p type of interaction looks like this. So this is a picture in their mind. And so this is, say, for example, some, say, sigma bond or something like that. So this logic, therefore, is important for communication between people and, say, them talking to each other or writing papers, and also explaining the behavior of even such simple molecules like say ethylene, which is shown here, which has only 4 atoms. But there are many electrons to share. And so this is a picture of the type which usually people will draw. And so they will talk about, say, some sigma bond between 2 carbons, and then also some pi bond, and then there is some sigma interaction between carbon and hydrogen. So this is a language which we use for expression. And so that language basically comes from combining these orbitals together, say, for example, in this what is called linear combination of atomic orbitals, and trying to solve Schrodinger equations and finding how electrons talk to each other and how do they talk to nuclei. Does make sense? So how many people are familiar with this type of terminology, and how many people know where these sigma and pi and these orbitals say come from? So maybe you can show your hands that I can have an idea, what is actually say we're having out of people who are remaining. So I can see that there are about half of you who actually have seen that. So 15 out of 30 or more have seen this type of language in their discussion, right? To some extent. Okay. So that is good. So let's maybe try to revise this question and ask a question about where these shapes come from. So why do we have these weird shapes? Why, for example, it is not square or rectangular here, or it doesn't have, say, maybe some more complicated shape like some spaghetti or something, but we usually operate with this type of shapes when we talk about probabilities of finding electrons between nuclei. So these points here are nuclei, and so these shapes represent probabilities of finding electrons. So that means that, say, probability of finding electron here is 0. The probability of finding electron between these 2 nuclei is very high, right? So this is what is the meaning of a bond between atoms. So this goes back to this angular momentum operator. And so this is why I thought that it would be useful to revisit this question, because this illustrates also the postulates of quantum mechanics. So let's talk about this angular momentum, because angular momentum actually is responsible of electrons, is responsible for these shapes, because they are defined by what kind of angular momentum electrons have in atoms when they come into some interaction and form some bonds between themselves. So, okay, so say, first of all, we need to come back to this notion of atoms. And electrons in atoms are particles in spherical or Coulomb potential. So basically, here we have some nucleus, which is small, but it is charged positively. And then we have electrons which are orbiting this nucleus. And so therefore, this is kind of classical picture, which is useful to describe using spherical coordinates and spherical potential, which has these variables like these angles phi and theta, and also distance r. So the same mathematics actually applies also to rotation of molecules, which you may be also encountering later. But in classical physics. What we have is, so this type of behavior, when something is orbiting something, is described using angular momentum. And so angular momentum for classical particle is introduced in this way. So we have a vector product of position and the momentum of these particles. So we have, say, a particle orbiting around, say, something, maybe on a spring, for example. So there is a force acting on it, and there is momentum in certain direction. And so we introduce angular momentum for this particle using this type of definition. And so you can see that this angular momentum is a vector which has these single vectors I, J, and K. And so as a vector system, it is represented by these three components, right? So it has X, Y, and Z components in Cartesian coordinates. So now, if we move to quantum mechanics, then what we need to do is to substitute these variables, i.e. position and momenta, by operators. And so the way how momentum is represented in quantum mechanics is this equation here. So for example, for momentum in x direction, what we have is a partial derivative in that direction multiplied by this complex number and Planck's constant divided by 2 pi. So this is the way how we introduce an operator instead of momentum. Momentum is a number in classical physics. In quantum mechanics, according to our postulate, number 2, we should be representing it by operator. And so how operator looks like is for momentum is it looks like in this way. So this is also a postulate. And so then we can write down our orbital momentum in a way of these quite complex operators, right? So these are basically derivatives over z or y, which are going to act on the wave functions. And in this way, we have our equations, which allow us to find real eigenvalues for our say operators. In this case, it is orbital momentum, which we would like to measure. So it is observable. So we would like to be able to calculate it. And so for that, we need to use our equation, which we postulated in postulate number 3. So therefore, we introduce these Hermitian operators for quantum angular momentum. Therefore, we transfer from classical representation of orbital momentum to where we didn't have these heads here, to this quantum representation where we substitute this momenta by the operators, and we end up with this expression here. So instead of a simple thing like a product of y and p, etc., now we have y multiplied by a product, by this derivative, partial derivative, and also multiplied by this complex number and h. So this is how it is written. And so then first thing which we need to do is to check the commutation relations. So why do we want to check the commutation relations? Because we would like to know whether, say, our quantum momentum as well as orbital classical momentum have 3 components, x, y, and z, in Cartesian coordinates. And so we would like to know whether we can measure all of them simultaneously, or we cannot. And so the answer to that question comes from calculating what is called these commutators. So we need to take this product and act on the wave function and find out whether this action, say, AB minus BA, or in this case, LX LY minus LY LX, will be giving us 0, which would mean that actually we can measure these components simultaneously, or it will give us non-zero. And so it turns out that it is non-zero. So this is what is written here. So basically, when you calculate this operator, what you find is that, let's say, this operator, when you act on the wave function, is giving you a non-zero value, which means that we cannot measure them simultaneously. So basically, if we know one of them, we cannot know, say, another one, or another two of them. Say, if we know Lx, we cannot know Ly and Lz. And so this is what is result of this test or check which we carried out on commutation relations. Now, another thing is we can try to find whether there is any other operator of orbital momentum with which there is commutation, which we couldn't actually measure simultaneously. And it turns out that actually each component of orbital momentum commutes with square magnitude of angular momentum. So L squared is a square magnitude of orbital angular momentum, which is written here. So if we sum up squares of all components, we get square operator of that. And so when we check, it turns out that actually for each of these components, Lx, Ly, and Lz, if we take a commutator with L squared, we get 0. Fantastic. So that means that actually we can measure simultaneously one of the components and L squared. So what is the conclusion here? That Lx, Ly, and Lz are not compatible observables. So they cannot be simultaneously eigenfunctions, and they cannot be measured simultaneously. And we cannot have perfect knowledge of any pair at the same time. Yeah, so this is what big physical result of that is. But the different components all commute with L squared. So L squared and each component are compatible observables, and we can find simultaneous eigenfunctions of L squared and one component. So this is mathematical representation that we can find simultaneous eigenfunctions of L squared and one component. So this is mathematical representation of this physical statement, which we're going to use now. Yeah, so how are we doing now? I think we made through, basically we used two postulates, right? So we introduced say some observable. We say, okay, so something is moving like that. It has angular momentum, so let's describe it quantum mechanically. Okay, so in order to do that, we need to introduce operators, check, say whether these operators commute, find out which of these operators commute between themselves, and therefore may have a common set of eigenfunctions or simultaneous eigenfunctions. So this is what the logic of this is. So how do you feel about this? I mean, can you digest that? For some of you, I guess it's very familiar if you did physics and were doing some atomic and molecular or advanced physics, but for some maybe more difficult. But we need to get common ground for all of you, because you'll be attending further lectures.
There's just one question that I had, was that do the various components of the angular momentum not commute due to the uncertainty principle?
Uncertainty principle is not the cause of anything.
Oh, okay. It's just
uncertainty principle is a result of the fact that actually they are not commuting. So therefore, you can find both of them with certain uncertainty, as to say, or with certain error, but you cannot know both of them exactly at the same time, right? So if you know one of them, say exactly at this, then you cannot know anything about two other components. If you know one of them with some uncertainty, then you can know some of the others with some uncertainty. So this is the logic of uncertainty principle, right? But this comes out of the mathematically, and so this is important that you kind of respect this mathematics, because people try to brush these things out. But in reality, without understanding where exactly mathematically these things come from, it's very difficult then later to do research, right? Because you don't understand the causes of things which may be happening in your simulations. And so mathematically, this comes exactly from this commutator, and checking the, say, whether these operators commute or they don't. So this is mathematical cause of what is going on. And again, it's important that actually, you realize that actually goes back to our postulates. So you need to kind of feel free to think in terms of, okay, so I hate this theory, and so I would like to develop another one, say better quantum mechanics or something, because I don't like these postulates, and so all of that is stupid, which is fair, but fortunately, this theory still describes quite a lot of things pretty well. And how do we know that? Because this theory operates with Hermitian operators, and so therefore when we calculate energies, for example, for some electrons in atoms or in molecules or in crystals, whatever, we can measure them experimentally because they are real number, and we can compare. And so it turns out that actually with quite high accuracy, we can predict what is actually happening. So far, actually, there is no kind of very huge discrepancy in terms of, say, quantum mechanics failing miserably to predict something, but interpretation. And so you need to realize that here we talk within some particular interpretation of quantum mechanics, right? Maybe different. And so there are, different communities and different people who are actually developing different interpretations of quantum mechanics, and they talk on different language. But for you as starting researchers, it is important to realize that the language which you are going to talk to most of your colleagues and peers is based on these operators, and you need to respect them, these operators, and understand where do they come from. Yeah, make sense?
Yes.
Right. Okay. So conclusion is we can find simultaneous eigenfunctions of one component of angular momentum and L squared. So this is what we have been talking about. So that means that actually we can measure both of them with high accuracy, or very high accuracy, simultaneously, right? So for others we cannot. And so conventionally, what we usually, in quantum mechanics, due to some reason, we choose what is called Z component. And we want to find what are their eigenfunctions and their eigenvalues. So meaning, say, how we can describe the angular behavior of these electrons or these particles, and how do we can measure their eigenvalues, or measure their values, as they say. So as you know, that component is usually defined by external field, but if there is no external field, whatever, say X, Y, or Z is the same thing. So now, here is some piece of mathematics, which for many of you should be familiar, because basically, this is how you represent say these things in spherical polar coordinates. And so in many, say, for example, if some of you did hydrogen atom in your quantum mechanics, etc., you should have seen all these equations, because we solve Schrödinger equation for hydrogen atom in these spherical polar coordinates, because it is easier than to do it in Cartesian coordinates. So we go from this XYZ to R, theta, and phi in these spherical coordinates. And so this is these variables are related in this way. And so it kind of looks a little bit frightening when we try to go from here, say where we have kind of relatively neat expression for our operator, to here, where we have and a more complex expression. But it turned out that actually at the end, it is easier to solve differential equations, which we are going to discuss in this coordinate system. And so it's important to realize that actually quantum mechanics is basically, or whatever you are going to do, say if you call it, oh, I'm going to use WASP in say calculating this and that. At the end of the day, what is WASP? WASP is a method how to solve differential equations. Right, so by making this statement in your paper, say in our calculations, we use WASP with this particular, say, plane wave cutoffs, etc. Basically, you tell people like yourself that, okay, so you have been solving some differential equations using some certain method, right? And so quantum mechanics, because of these operators, is a system of differential equations. So this is what we are having here, operators which are derivatives. And so therefore, when we construct our equation, which we postulated in postulate number 3, that we want to have operator acting on the wave function, and this gives us eigenvalue and eigenfunction. So we basically construct a differential equation. And so solving this differential equation for, say, systems like atoms, which have spherical symmetry, is easier in spherical polar coordinates. And so this is why we go there and construct this type of expressions. So we're not going to go through that, but I mean, this is just to give you some idea what is actually, what is going on in this mathematics. So now for LZ, so if we take, let's say, our component, Z component of angular momentum, and try to represent it in spherical polar coordinates, we arrive to very simple expressions. So this, instead of this expression for LZ, which we have in Cartesian coordinates, we have now this operator. So this operator is basically partial derivative by this angle phi. So basically, this is a simplification, what we get out of using spherical polar coordinates for representation of this operator. And so now what we can do is, okay, we need to use this operator, and then we would like to find its eigenfunctions and eigenvalues. So this is what we postulated initially in our postulate number 3, that if we want to know something about this LZ, so in order to do that, we need to solve equation of this type. So we need to act by operator on the wave function, which represents behavior of our system in this phi geometry. And we will have some number here, which should be real. So because this equation should be Hermitian, and the wave function. And so this is how we said we are going to deal with this, finding out about these variables. Okay, so as I said, this means basically solving some differential equations. So we have our operator here, which is a derivative. We don't know how this wave function looks like. We postulate that we have some coefficient here, which is some number multiplied by Planck's constant. We use Planck's constant because Planck's constant has the same, it was saying somewhere here, the same units as the orbital momentum. So therefore, it's just units which we introduce here. What we want is to find what is the value of alpha and how this wave function looks like. And so this differential equation is easy to solve because if you have the derivative multiplied or act by it on this wave function, so when you know that actually, and so this gives you the same wave function here and some coefficient, you know that the wave function should be exponential. So this is the only way how you can satisfy this type of equation. So when you act by this derivative on this wave function, so what you will have is some coefficient in front here and your exponent, because when you take a derivative of exponent, you get again exponent. So this is simple. And so we know the shape of this wave function. This wave function should be exponential. And then we apply this other postulate. So we apply the postulate that the wave function should be normalized. So that means that actually when we take an integral of this wave function over the whole space from, in this case, the angle should be changing from 0 to 2 pi, we should be getting unity here. Okay, so this is very powerful method because, okay, this allows us to find what is this coefficient A. And so because of this normalization condition, what we find is that this coefficient A is equal to 1 over 2 pi square root, right? So therefore, we know that this wave function should look like this. So this is, relatively simple solution of differential equation. And then the next thing is, why do we have quantum mechanics? So this is an important thing, right? So why it is quantum? So what means quantization, right? So far, we didn't have any quantization, so we didn't postulate any quantization at all. I mean, we didn't say anything about that things should be somehow quantized. So this comes from these boundary conditions. So this is an important thing to understand. So the wave function must be single valued, all right? So this is kind of simple condition which we impose. So if we kind of go around the full circle, we take this phi plus 2 pi, we should be getting the same wave function. Okay, so if we impose that condition, it turns out that actually the only way this can work is if this coefficient alpha, which we have an exponent here, is just an integer number. And so this integer number can take values like 0, plus minus 1, plus minus 2, plus minus 3. So suddenly, we are in quantum mechanics because we have got quantization as a result of, say, application of our postulates, getting differential equations, solving these differential equations. And when we solve differential equations, we always need to apply boundary conditions. And we apply these boundary conditions and we find, okay, so if we want to do that, actually, we need to be getting some eigenvalue. And so that value, m, should be integer. And this means that actually our system is quantized. So that is an important thing. So what it says is that angular momentum about the z-axis is quantized in units of our Planck constant divided by 2 pi. And so therefore, we have that our operator Lz has this value m divided by, m by multiplied by Planck's constant. Now, the question is, actually, I missed that point, but now it is 2:06. So do you want to have a break? Because usually we would have a break during these lectures. And actually, when these lectures will be in person, you will also have coffee and biscuits with that. Unfortunately, I cannot provide that now. Do you want to have a break for a couple of minutes? And then we carry on from then? Okay, so let's have a break till, say, 2:15 to give you a chance to get your tea or coffee. Meanwhile, if people have questions, So what we are having here is we just have an example of application of our postulates to a particular question of about how we deal with understanding what is angular momentum for, say, some particle which is moving, say, electron moving in some spherical potential. And so what we found is that LZ component is particularly easy. So it has, it is quantized with this quantum number m, which has this integer value as a result of application of boundary condition. And so boundary condition is that the wave function must be single valued. So this is simply a sensible way of saying that. Again, so in the same way as I was saying before, you can try to construct quantum mechanics which will not be satisfying these conditions. For example, wave function is not single valued or something like that. And so this will look differently. And then you can compare it with experiment and measure things and find out whether it is a good way forward or not. So far, applying this single valued condition has been proving quite useful. Now, then we need to look at what happens with L squared. So this is more complicated. Again, we need to solve the same postulated equation. So meaning that we have operator operating now on the wave function of two variables, theta and phi. We have now, again, some coefficient here, which we don't know. We need to find out. And then h bar squared, which provides our units, but also provides some value because you know that, say, Planck's constant is quite small. And so that means that actually eigenvalues, which we are having here, which are some integer numbers multiplied by the Planck's constant, are going to be also quite small, which also tells you about something about the limit of quantum versus classical. So if you have classical particles, simply what you have is much bigger values, which then you can fill with classical techniques. So then we have this wave function here again. So this is our equation for eigenvalues and eigenvectors. But now operator is much more complicated because we went into spherical polar coordinates. And so L squared is represented in this way. And so we can write the solutions in the form of, say, separating variables. So in the form of, say, function which depends on theta and function which depends on phi, sorry. And so this wave function can look like that. So we know already solution. So this is a standard way of, say, separating variables in solving differential equations. And so now what we want is to find how this our another wave function, which is a function of only theta, can look like. So that is becoming quite complicated differential equation, which has a name of Legendre, who is a French mathematician who was looking at these equations. And also, we involve another gentleman called Frobenius, who actually developed a method of solving them. So we are not going to go through these maps, but what we are going to say is that after some substitution, say if you, this is usually how you deal with differential equations, you arrive to a little bit simpler form. And in this simpler form, you find that actually in denominator, you have this 1 minus mu squared. And so this value, 1 minus mu squared, it diverges if this mu is equal plus minus 1. And so therefore, we need to impose a condition, so which is another boundary condition, that solutions which we need should be finite at these values. So we should not be getting divergence as a result of that. So this is, again, a sensible way of dealing with it. Otherwise, you know, we get infinities, and so we cannot get anything. And so it turns out that, again, we arrive as a result of that to quantization because the only possible value of, say, this our eigenvalue beta here is that if it is satisfies the condition that beta is equal L plus 1, so this is a familiar combination many of you have seen, where L is equal 0, 1, 2, etc., and it is greater than square modulus of M. And so, sorry, the modulus of M. And so this is a gauge quantization condition. So in this case, quantization of this eigenvalue of beta comes from requirement that actually our solutions are finite at, say, mu is equal plus minus 1. So basically, this is a mathematical requirement which allows us to get values which makes physical sense, meaning being real, finite values which can be compared with experimental results. And so this is what comes out of solving this differential equation. So what we see here, so basically we build up some theory which you are going to use, which is quantum mechanics. That is based on postulates. So these postulates tell you about wave functions and how to find them, and also how to find eigenvalues. So we need to solve equations. So these equations are differential equations. When we do that, we find that actually our eigenvalues are quantized with respect to some, say, quantum numbers. And so these equations or these solutions are written in this way, and they are expressed in what is called Legendre polynomials. And so this is where basically the root of shapes which we have started from, these spherical shapes or these dumbbell shapes, etc., comes from. This is how these mathematical solutions of our equations for angular momentum basically look like if we construct them in space. So first of all, we have eigenvalues. So these eigenvalues are expressed in this quantized way. So now we have this quantum orbital quantum number and magnetic quantum number, which are represented in this form, which many of you have seen in the past. And then we have also the way how these wave functions can be represented in space. And so these wave functions of these, which are common wave functions, simultaneous wave functions of L squared and Lz, because these two operators commute. And so that means that we can measure them simultaneously. So they are represented as spherical harmonics. And so these spherical harmonics are these wave functions or functions of these Legendre polynomials multiplied by this exponential wave function, which is solution for Lz. So these Legendre polynomials are basically the cause or the reason why we are having the shape of our orbitals, which we are talking about in this way. So these shapes are here, right? So if we try to draw spherical harmonics, we see that, say, for different values of our quantum numbers, so if L is equal 0 and M equals 0, so it is spherical. And so, say, for example, for L equal 1 and M equal 1, it has this type of shape in space of theta and phi. Yeah. So basically, what it tells you that, okay, so if we try to solve, say, our equations for, say, orbital momentum in spherical polar coordinates, we arrive to this type of solutions And when we try to draw them in space, then they have these interesting shapes, which are kind of donuts or some dumbbells, etc., which represent how they actually behave as a function of, in this case, angular variables. And so the physical meaning of that is that if we say, okay, so this is our electron, which behaves in this way, or some quantum particle, this defines the square modulus of this wave function, defines the probability of us finding this, say, particle in this particular part of space at this moment in time. And so this is what how this whole story works. So obviously, to understand it better, say, I mean, you can see all these shapes coming out of these, say, spherical harmonics, or our solutions for this orbital momentum L squared and Lz. So what we need is, in the remaining part of time, we need to go to basically hydrogen atom, because hydrogen atom is the next step. So before, we have been just talking about some abstract kind of thing. Okay, so here is some angular motion of some particle, and so let's see how it is quantized. So now we have a real particle, which is now hydrogen atom, which has a nucleus and which has an electron. And so we would like to apply all of these mathematics again to now a similar spherical type of system. Right, so in this case, what we do is that we nail our nucleus for any of these hydrogenic atoms. So we nail it, and then we say, okay, so electron is moving around somehow. And so what we would like to say is that, okay, so now we have what is called central potential, which is described by this Coulomb interaction of our electron with this nucleus, which may have a charge Ze, and operator which describes this behavior is Hamiltonian operator. So it includes kinetic energy of this electron, which is now represented also in form of operator. So we have this gradient squared, this Nabel operator here as our operator describing kinetic energy. And we have also potential energy of our electron, or say, moving in the spherical central field of our hydrogen atom. So there are, say, those of you who did atomic physics, etc., they know that actually it's an approximation, because electron, although it is lighter than the nucleus, but still what you need is to consider reduced mass, and so nailing the nucleus is actually quite a strong approximation. But in the first approximation, we can do that. And then, so there are these various approximations which can make. So you can see that, say, the mass of the nucleus is, say, 2,000 times bigger than the mass of electron, but you still make some error by assuming that nucleus is completely nailed, and so it is not moving at all. So in reality, you need to be using this reduced mass for solving these equations. But never mind. So let's look at, first of all, at how to solve the Schrödinger equation for this hydrogen atom or hydrogenic atom. So now we have the same thing. So we have our electron moving in spherical polar coordinates. So we need to express our Hamiltonian in this way. So again, we have a kinetic energy, which we represent in a this complex way of these coordinates r, theta, and phi, and we have potential energy. So potential energy is here, which is our Coulomb interaction, and then we have a wave function, which is now dependent on coordinates on the distance and two angles, and we need to find energy, and we need to find the wave function. So the same equation which we postulated for, say, finding properties of our systems. In this case, the property is energy, which we would like to calculate, and the wave function of our system. And so in order to do that, we need to solve equation of this type, acting by operator on the wave function and finding eigenvalue and eigenvectors. And so if we do that, and some of you have gone through this solution, what you find is that basically the advantage of being in polar spherical coordinates is that you can separate variables. So, this is the same thing as you should have been doing in mathematics. So when you try to solve differential equation, so what you want to do is to separate variables as far as you can. So you don't want to solve your, say, your differential equation for all, say, 3 or whatever variables at once. So you want to represent your function as a function of separate variables. And so this is what you can do in spherical polar coordinates, but you cannot do in Cartesian coordinates. And in spherical polar coordinates, you can represent your wave function as a product of the function which depends only on the distance, and then the wave function which depends only on the angles. And so this angular wave function is the spherical harmonics wave function. So this is a function of our angular momentum operator. And so it is now becoming part of this total wave function of, now it is electron wave function in hydrogen atom. So we know that what are eigenvectors and eigenvalues for L squared operator. So if we act by L squared operator on our wave function, so we get these values here, LL plus 1, multiplied by the spherical harmonic. So that is already we discovered from our solution for angular momentum. And so now we can try to simplify our equations on the basis of that knowledge. And what we find is that we find one equation which is dependent only on coordinate r, or the distance between electron and nucleus. And then we have solution for the previous equation, which depends on coordinates theta and phi, which are the spherical harmonics. So we already know this solution. So what we need is to find only solutions which depend, or solutions for this wave function, which is a radial, what is called radial wave function. And so here is an important result. So if we do that and we solve these equations, what we find is that all our solutions, which we find for this equation, they depend on a distance exponentially. So you can see here that what we have is an exponent. So there is some coefficient here, and then we have exponential decay of the wave function as a function of distance from the nucleus. And so this is another very fundamental property which you are going to use all the time. So these wave functions of atomic orbitals at long distance from the nucleus, they're exponentially dying. So close to the nucleus, they may be having quite complicated behavior, they may have some oscillations, etc. But when it comes to long distance from the nuclei, so they are dying exponentially. And so this is the probability. This means that the probability of finding electron, say, far away from nucleus, and so that means maybe 1 angstrom, 2 angstrom, 3 angstrom from nucleus, is exponentially decaying. So this is a very important thing to remember. So all wave functions behave like that. And this comes from simple solution of Schrödinger equation for hydrogen. So for hydrogen, the ground state of the electron in hydrogen, when it is at the lowest energy, has this shape. And so this is a constant multiplied by exponent. And so it is decaying exponentially with the distance from the nucleus in this way. So this is a wave function of this hydrogen atom if you make a cross section of it along the distance from the nucleus. And so that is fundamental because if it is not hydrogen, but it is, say, zirconium, or it is uranium, or any other atom, if you take electrons in those atoms close to the nucleus, they may behave in a very complex way. But as you get out, and so you consider a longer distance from nucleus, these electrons always, say, the probability of finding them, say, close, say, around this atom is decaying exponentially. And so that is a property which is used all the time in quantum mechanics. Also, when you talk about tunneling of electrons, etc., so you encounter the same type of behavior because electrons tunnel, and the probability of the tunneling decays exponentially with the distance, etc. So this exponential behavior stems from basically solution for Schrödinger equation, and this is the only equation which we can solve exactly. So this is important to understand. So as soon as we get more electrons, say, for example, we have 2 electrons for helium, or we have 3 electrons, we cannot get exact solution. So we always deal with approximate solutions. So the only equation which we can solve exactly is this Schrödinger equation here. And although it is very complex, as you can see, but mathematically, because we have already solved our, we know about Legendre operators, and we have solved our equations for angular momentum, and we can also solve differential equation of this form for our radial wave function, although it is kind of looking frightening, but we can find a solution for it. And so that solution basically for example, for the ground state looks like that. So it is more complex for excited states. So the lowest energy eigenvalue, as many of you know, for hydrogen atom has this value. So, and this determines the shape of the wave function. So the wave function for the ground state is spherical, as we know, and it has also this coefficient here, which is Bohr radius. And so the probability of finding an electron in the hydrogen atom has a maximum close to the this Bohr radius. So this is a very fundamental thing to understand, because this determines all our sizes, right? So the way that the fact that you are whatever, say 6 foot high, is determined by the fact that actually we have this combination of fundamental constants here, which is called the Bohr radius, and it has certain value, right? So it has this value here, so which is 0.529, 10 to minus 10 meters. And so then that determines the scale, right? So now what is happening is that you put these atoms together, there are plenty of them in your body, plus to that carbon, which is a little bit bigger, and then say maybe nitrogen, etc. So all of that makes you or me. And so if we put all these atoms together, we get our size. And so the scale of that size is determined by this fundamental value of hydrogen atom, because atoms, when they combine together, they don't penetrate into each other, so they kind of build up volume. Because when they come close to each other, they repel each other, or they form these bonds. And so this scale is a fundamental scale, therefore, because it's like a Lego, right? So what you build molecules out of atoms. Atoms have certain sizes, and so then you build DNA out of these molecules, and then you build your tissue out of these molecules, etc. And so this is where the scale of all things come from. Is that clear? So that is the result of us basically solving some differential equations on the basis of postulates which we made. Right? As I said already before, you can make different postulates, you can arrive to different differential equations, you can solve them, you can find alternative quantum mechanics. Say the quantum mechanics which we are talking about at the moment seem to work pretty well because we have been able to calculate the value of this Bohr radius to this very high precision. So this has been measured experimentally, right? So it has been determined. And so it seemed to work reasonably well. And then there are also some corrections which come from relativity and uncertainty, etc. But basically, which are shown here. But basically, we know these values with very high accuracy. And so that is an important result of, say, us being able to solve these equations. So if you consider higher states of electron states of electron in hydrogen, because we know that actually this electron may be in the ground state, but it may be in some excited state. So these states are quantized with a principal quantum number n. And so if we look at the quantum at solutions, then you can see that these solutions are more complex, right? So they involve some polynomials, which are called these Legendre polynomials, but invariably they involve this exponent. So this is what I was telling you. So basically any solution, even for complex atoms or for high excited states, it may be complex near the nucleus. And so this is how this polynomial may look like for, say, D states, states with n equal 3, etc. But far from the nucleus, they will be exponentially decaying. And so that is a fundamental property which we use all the time in, say, solving our equations for molecules, crystals, and more complex systems. Okay, so then there are these usual things which you need to do. You need to show that you need to normalize these wave functions. You need to show that they are orthogonal, etc. So this all comes from postulates. But the major thing which you need to understand is that by solving these Schrödinger equations or equations which we postulated, we find some quantization. So quantization comes usually from boundary conditions. For atoms, we have 3 quantum numbers and then spin, which we didn't talk about. And so the energy as well as orbital behavior of electrons are all quantized in this way. And so we also know how the wave functions of these orbitals look like. And so they, for hydrogen, so they have these mathematical forms. And so now, if we can use these mathematical forms, and this is what we do, and this is what, say, for example, Popol and people like that got the Nobel Prize for, because they devised basically computational methods, how using these, exactly this type of wave functions, to try to explain behavior of molecules. Right? So basically, you can make combinations of the wave functions, trying to explain the behavior of molar electrons, like in the molecules. So these are linear combinations of atomic orbitals, and in this way, introduce all these notions about chemical bonds and describe the behavior of electrons in molecules and solids, liquids, and other systems which contain many electron systems. So this is exactly what we are going to talk about at future lectures. So next time, I think Dave is going, hopefully he'll come along. And so he will talk to you about how we deal with many electrons. So we need to introduce one electron approximation, introduce Hartree-Fock approximation for that, and then move to density functional theory, how, say, the way of dealing with these many electron equations. So an important thing to know is, which many of you know, is the notion of orbitals. So orbitals are basically these solutions of, say, equations for atoms like hydrogen. And so they are classified in a way we classify angular wave functions. And so what we're talking about and the language which we use is related to these notations here, S, P, D, F, G, etc. So we talk about S orbitals, which are kind of spherical, and then we talk about P orbitals, which have some dumbbell forms, and then we have D orbitals, etc. So this is common language, which comes from spectroscopy from 100 years ago. And so S and P and D and F, etc., they stand for spectroscopic notations of, say, hydrogen atom and some other atoms, standing for sharp lines and principal lines, diffuse lines, and fundamental lines. And so when people were trying to explain the behavior of these spectra, they have introduced some phenomenological notations like sharp, principal, diffuse, and fundamental, which you can discuss later. But it's important to understand that what is the origin of this SPDF, which basically we use as our language all the time, right? So you can, when you'll be describing behavior of electrons in some, say, crystal, you'll be saying, okay, so the bottom of the conduction band of this material is determined by D functions of titanium, for example. And so this is how you'll try to convey what is actually going on there to, to your peers or to people who are going to read your papers, and they will immediately understand what you are talking about, because they understand this language, so they know what are D functions. So D functions are the functions which are corresponding to angular momentum of some titanium electrons with orbital quantum number equal 2. And so P functions correspond to orbital quantum number equal 1. And so they have these shapes, etc., etc. And so this is, how the theory is built. So these are these famous shapes for these p orbitals and say d orbitals, these are exact representations of these wave functions in space in x, y, z, and these are kind of more general shapes for hydrogen wave function, which form that language which I just mentioned. Okay, so this is kind of general overview of what I felt, you need to maybe remind yourself before starting talking about basically practicalities, and so how you are going to deal with, say, mainly initially solving Schrödinger equations for crystals, because in the next lectures you'll be talking about Bloch functions and periodic boundary conditions. And say then how plane waves can be used also for solving these equations, etc. But all of that stems from this one system, which is hydrogen, for which we can solve these equations exactly. So for all other systems, these will be some approximations which we'll be discussing. Okay, so I guess I can stop here with this overview, but I would be happy to answer any questions you may have meanwhile. So was it useful and clear for you?
All very clear. Thank you.
Sorry?
I said all very clear. Thank you. Very clear.
Oh, thank you. Well, it's kind of clear, well. Yeah, thanks, Saida. So any other questions or comments you'd like to make? So I guess, as I said, many of you have different backgrounds, I can see, which is not surprising. But you need to learn the same kind of common language, which you'll be then using for, say, your research, but then making presentations, for example, for student day in TYC or at conferences, etc., which basically stems from these notions which we were just discussing.
I have one question. Do you have any textbooks or papers which you would suggest, which we want to cross-reference and make sure we get some of these ideas down?
Well, as you know, quantum mechanics is about 100 years old. So therefore, there are many books and
are there any in particular that you recommend?
Papers, etc. I like one particular book which I can share with Karen, and say she may want to put it on the web. But basically, my advice is usually to go to the library. What many people forgot already about, but it's a good place. There are shelves with books, and it's better to. And there are lots of quantum mechanical books on this topic. So, but many people have different backgrounds, and they like reading books in certain ways. So, by browsing through these books, you can find one which is better for your background and the way how you have been taught in your university, and how you understand. For example, Atkins, physical chemistry and quantum mechanics and atomic and molecular books, people find quite useful. They have been written for chemists, but they contain more or less the same information, maybe with less mathematics. But then, there are more rigorous books which also involve some historical aspects of the development of quantum mechanics, etc., and experimental data involved, which I will share with Karen, one of those, which I like particularly, but you may like a different one. And so there is no universal kind of textbook for the module, but for these atomic and molecular things, there are quite good books, which, as I say, I will share one, but you can find many others. Also, if you look on the web, and so Google things and say ask particular questions, so there are plenty of lecture courses, as well as YouTube lectures which have been recorded by various good people, which you can also watch and understand from that perspective. So it's a huge variety of things. As I say, it should be somehow related to your background and how do you perceive these things, and which kind of presentation you like more. Does it make sense?
Yeah, thank you very much.
Okay, other questions? Fine. So if there are no further questions, then I guess we can stop here. It's almost 3 o'clock. I mean, I didn't go through all the equations, but I feel that it may be not necessary. If you picked up the main idea, you'll be going through quite a lot of this in the next lectures, but don't despair, because some of you may have maybe some, say, different mathematical background. So there will be, say, physical explanation, and so you need to pick it up. But if you are curious and you would like to kind of understand all the derivations, as we just discussed, there are books and reviews and say lectures, etc. You can go through and get to the bottom of what has been said. All right, guys. So good luck with your module. So if you have any questions, thanks to Karen, you can come to her, or you can come to me because I'm organizing this module, and so I'm responsible for setting up the syllabus and finding these lecturers who are going to give you. But these lecturers are, very good researchers with big experience. So please come and learn from that in person and talk to them. So see you soon then.